Hello everyone, I welcome you all again to this online NPTEL Field Structural Geology course. Today we are at our lecture number 3 of the first week, and we are going to learn the very basics of structural elements. So what we are going to do in this lecture, that we will talk about different planar and linear features that we see in the rocks, and we will also learn how to take their measurements, or in other words how to record their attitudes in the lab notebook. So, to start with, these are some terminologies as you can see here, and these are the things that when we are in the field we talk about this, we use these terminologies very frequently. And once a group works together, then maybe someone is measuring data and someone is noting it, and if you are there, you will always hear these terminologies they are communicating through. So, what are these? What do they mean to us, and how we can distinguish them one after another and can take their measurements is the aim of this lecture. But before that, what are structural elements and why it is important to look at? We know that in field the exposures that we see, they are not continuous, and we have seen actually in our previous lecture that we have some exposures in Ferighat, then in Harindugri area we have some exposures near the river bed, then somewhere in the Chitrakoot hillock, then some exposures along the Lokjharia Nala. We did not see continuous exposures, but we have to construct the lithostructural map. To do that, we can have some clues from the orientation of these rock units. Now, orientations of what? That is something that we are going to learn in this class. There is also one point that not necessarily all exposures you can reach and measure. For example, the exposures that we saw at the middle of the river Subarnarekha, it is extremely difficult to be there because of the velocity of the stream, and also you do not get access, the area is pretty dangerous. And then there is one more important aspect, is that the rocks are not deformed by a single deformation. Given the history of the earth, rocks may deform in multiple times. So, one feature is overprinted by other feature. So, it is the challenge of a geologist to identify these features, then separate them out, and then measure and plot them for subsequent interpretations. So, these are the very basic motivations that we need to understand, or we need to learn, that structural features are very important, or structural elements are very important for any geological field work, not necessarily only restricted for structural geology. There is also one important part, that once we see these structures in the field, given the depth of these structures, we only see their surface features, or in other ways we mostly see the 2D features. The maps we prepare, they are 2-dimensional maps, but geological structures are 3-dimensional. It is also important that through these measurements we can have an idea of their 3-dimensional features and orientations. Talking about structural elements, we can classify them in broadly 2 different ways. One group is planar elements and another group is linear elements. In the planar elements, we consider different planes, where we have bedding planes, different foliation, schistosity, cleavage planes, etc., etc. And in the linear features, we have, say, some geological imaginary directions like fold axis, but we have some physical directions like striations due to fault movements, we have mineral lineations and many other things that are considered as linear elements of structural geology. But why we have to measure them? Because we know from our first year undergraduate courses that sediments, they do deposit along horizontal planes. So, they should remain horizontal, and if they are horizontal, we know they are all over horizontal. That is true. Even the sediments that got lithified, we see them as horizontal. For example, here what we see here, we see a photograph of a vertical section. This is a photograph from Chitrakoot. Chitrakoot is from Madhya Pradesh. Okay? So, this is the sandstone formation, and what we see here that in this vertical face, that is, this is the vertical face, and we see the traces of these planes are sub-horizontal, and this is how exactly it should be. But what we see in field in most of the cases, because these beds or these rocks are deformed, we often see that they are not horizontal. For example, here we see this is the exposure of second quartzite band at Lokjhariya Nala, and we see here that this plane, if I consider here, this is almost subvertical, or all these planes that we see here or here, and the traces here we can certainly see and confirm that these planes are not horizontal. So, there are possibilities that beds not necessarily are horizontal, they can rotate, that means they are often tilted, and if they are tilted, then of course, we need to know that how much is the tilt, and if we know how much is the tilt, and if the tilt is constant throughout a region, then we can interpret in a different way, and if we know that no, the tilt is varying from one location to another location, then we do interpret them in another way. To talk about the other features, that is the linear structures or linear elements. So, here is a photograph. So, this is a mica schist again from the Ferryghat. We clearly see that apparently this surface is kind of wrinkled, right. You can identify that these features, these are actually known as crenulations, but other than this there are some mineral grains, and through these mineral grains you see that some shadows have formed. So, we have kind of a lineation along this direction, some linear features, and these are crenulations. So, crenulation axis are these. So, in a single exposure we see two sets of lineations. One set is crenulation axis and another set is pressure shadow lineation. Now, something is important to understand here that I was talking about a few minutes before. So, if these are the crenulations, then certainly the principal compression direction should be in this way, and if these are the pressure shadow direction, this is the mineral and this is how the pressure shadow is developing, the stress axis, the principal compression direction of stress should be in this way. So, clearly these two are not matching each other. So, there must be two different deformation, and to understand that there are many other aspects to understand this, but at least for this particular example that I am giving, it is important that we need to measure their orientations, plot them in the StereoNet, and then figure out that what has happened. Is it matching with something or is it not matching with something? If it is matching, then what could be the interpretation? If it is not matching, then what could be the interpretation? So, interpretation is always important because that is the primary aim, the way we go to the field, and to make better interpretations of our observations, it is important that we measure the data in the field, or we identify the different structural elements and do the measurements. Here is another example. This is a vertical face. Here the pencil is the scale, and you can see the crenulations here. So, these are the crenulation axis, and you can also see another set of lineations. We will learn about it. These are called striping lineations. So, again we have to ask questions that why it is so, and to answer this we have to come and do the measurements. What we have seen that we can have linear features and we can have planar features, and these are nothing but some geometric descriptions. So, to understand this better, let us talk about three basic elements of geometry. One is point, the second is line, and third one is plane. To define a point, you need one set of coordinates, then a distance and direction from reference point. You can get a point by the intersection of two lines, and you can get a point by intersection of three planes. In a very similar way, but in different aspects, you get lines by two sets of coordinates. You can define a line by two different points. The distance from a reference point and the direction of the line can define a line, and intersection of two different planes can give you a line. The planes you can define by three sets of coordinates, and it can be defined by three different points. It is defined by the distance and direction from reference points or lines, and defined by two intersecting or two parallel lines. These we have learned in our school, and we actually use this concept to get all the structural measurements. So, in the structural measurements, we do measure things in two different planes. One plane is the horizontal plane, where we can define north, south, east, west, because this is measured on a horizontal plane. And all measurements that we do on a horizontal plane, we refer them as azimuth. And when we do measurements on vertical planes, we refer them as inclination. So, azimuth is measured with respect to north, or when we use compass, we generally say that this is 0. So, measured along a horizontal plane in degrees. So, we have north, and then this is a horizontal plane you can guess, and then of course, you have the entire full circle to come to 360 degree, which coincides with 0 degrees. So, 90 degrees defines east, 180 degrees define south, and 270 degrees defines west. And of course, there are many degrees in between, and this is how we refer. In case of inclinations, we do things in a different way. So, we have trace of the horizontal plane. So, you can think of this, and then on the vertical plane. So, you can imagine that this is a vertical plane. We can have measurements. This is 0, because this is horizontal line. The inclination of this line is 0 degrees, and then you can come to 90 degrees. And then again you can have another set of lines in this side, where you can again achieve to 0. And therefore, if you remember in the clinometer or Brunton compass, we have seen that 0 to 90 and 0 to 90. Okay. So, we have azimuth, where we measure things along the horizontal plane, and we have inclination, where we measure things along the vertical planes. So, let us see how we can bring these two things together to define structural elements, both linear and planar. First, we will talk about the planar features, and in planar features we have three distinct terminologies that we use for measurements. One is strike, second is dip or dip angle, and third one is dip direction. There are tricks where you do not have to measure dip direction. If you know strike and dip measured in a particular way, you can get dip direction automatically. So, let us talk about what is strike or what is strike line. So, this is a bedding plane, you can consider this, or this is a planar feature which has a slope or which is inclined or which is tilted. Now, this plane is an imaginary horizontal plane. So, if I have a tilted plane like this and I can consider an imaginary horizontal plane, then the tilted plane will meet the horizontal plane along a horizontal line. So, we get a line and this is the line and this line we define as strike line, this is the line. So, the strike line also stays on the horizontal plane. So, if the strike line is on the horizontal plane, we can measure the orientation of this horizontal line with respect to north, and the angle that it makes from the north is the strike. There are many ways you can define strike of sloping or inclined bed, but you can read them from the books. I wanted to clear the concept. We will see later how we measure this and how we record this in our notebook. The dip angle is essentially the slope or inclination of this inclined plane that we are talking about. So, again we have this inclined plane, I have oriented it differently so that you can figure it out. So, we have then the inclined plane and the horizontal plane is intersecting the inclined plane. So, the angle it makes that you measure in a vertical direction, this angle. So, this is the sloping plane, you have the horizontal plane and the angle it makes is the dip angle. So, in this case you can see that this is the horizontal plane, imaginary horizontal plane, this one. So, the angle it makes is this one and this is known as the dip angle, and the direction the bed is inclined to or the direction it is sloping is the dip direction. Okay. So, if you use the right hand rule for measuring strike, it makes life easy, we will see it later. To define these things, we have definitions here, we have strike, we have dip angle, we have dip directions. Sometimes you get the sections in a different way, that you cannot measure the dip along a vertical direction. So, this time we call it apparent dip. With different apparent dips, you can actually get the true dip. This has been taught in the structural geology course. So, you can go and refer that. I am not reading all these things here, but you can get through this. I repeat, there are many ways of defining strikes in word sentences, but it is important that you get the understanding of the terminology is clear, so that there is no problem to express yourself. Let us talk about the linear features, the trend, plunge and pitch. So, I have the same inclined plane here, and in this plane we see some linear features, okay. Say some stretching lineations are there. Okay. So, again we need to have one imaginary horizontal plane that is there, and then the intersection defines the strike line. Now, you have these lineations, you have this inclined plane, then you have this pen, you can imagine the stylus as the lineation, and if you move this stylus vertically and where it meets the imaginary horizontal plane, then it makes a line, it intersects the imaginary horizontal plane along a line. The azimuth of this imaginary line is the trend line, okay, the trend of this linear feature. And what you get then, the amount, the angle that you have to move from this plane, inclined plane, to make it horizontal is the plunge, which is defined as B. Okay. Then there is one more important terminology, that is pitch. The pitch is essentially the angle that you measure between the strike line and the linear feature on the planar feature. So, here we are measuring it here, that means on the sloping surface we are measuring it. So, to show you, this is plunge, this angle that I am making to meet it horizontally, imaginary, and if this is the strike line, then if I take it this way along the plane, that gives you the pitch. Sometimes people refer this as rake as well. So, this is how it has been defined here. You can get things out of this slide. Now, once we understood what is dip, what is strike, what is trend, what is plunge, what is pitch, now it is time to understand or know that how to measure them in the field. So, in this slide we have some instructions one after another, and we generally follow something called right hand rule. However, one of the TAs, Rajiv, will demonstrate you how to do that directly in the field. Have a look.
We are going to take some essential field data regarding the geometry of the orientation of these planes. So, as far as field concerned, the most important to the data we gather are the strike and dip of planes. Now, strike is basically the intersection between this inclined plane and imaginary horizontal plane. So, if there was an imaginary horizontal plane that was intersecting with this inclined plane, that would give us the strike line of this plane. Now, we have particularly selected this spot to demonstrate the orientation of this plane, and that is because of this natural water present here. As we know that the free surface of water always maintains its horizontal level. So, the marking created by this water and essentially this water level will give us the strike line. So, we can physically see the strike line here. So, that is the beauty of this spot. So, as you can see that the strike line is oriented like this. Taking the measurements of strike line, we need a direction, and as you know that any horizontal line on this plane will be a strike line as long as this plane is remaining its inclination constant. So, for measuring strike line we need a direction, and for direction we are again going to measure that with Brunton compass. We will follow the right hand rule, which is the most convenient way to measure this kind of data in field. Now, we measure the azimuth of strike line, which is essentially the angle measured in the horizontal plane from the north direction.
So, now I am placing my right hand over the sloping surface, and as you can see the four fingers except the thumb, they are along the dip direction of the slope, and I am placing my thumb in such a way that it will follow or it will be parallel to the strike of this plane. Now, after placing the right hand, when I am placing the Brunton compass, it should be done in such a way that the long bridge or the sighting arm of the Brunton compass or the crown in a clinometer should be placed following the thumb, pointing away from us.
The flat surface in contact of the inclined plane. So, first we need to make sure that this Brunton compass is touching the inclined plane exactly continuously along this flat edge. Then we need to rotate this Brunton compass accordingly while it is touching the plane, such that the bull's eye inside this Brunton compass dial will give us the exact center. I mean, the bubble present inside the bull's eye will be exactly in the center. That would give us the horizontal plane we are looking for. So, what I will do now is that I will touch this base, this flat edge of this Brunton compass on the inclined plane, and then accordingly rotate my compass, and I am seeing from here where the bull's eye is exactly coming in the center, the bubble is coming in the center. Now, as I find the bubble in the bull's eye is in the center, I know that I have found the strike line, and I can measure that anywhere on this plane. Now, I need to find the magnetic compass reading from the dial, and the north point towards the direction it is pointing will be my azimuth of this strike line. For this case, I am getting a reading of around 300. That means the trend of this strike line is 300, and exactly opposite to that is 120. So, we can say that the trend of this strike line is 120, 300. Now, we are going to measure the dip of the plane. So, now as we know this is the strike direction, we will place our Brunton compass exactly like this with the flat edge merely vertical on this surface, and you have to make sure that the flat base is touching perfectly on this surface. Now, as the surface, I mean the flat edge of the Brunton compass is exactly aligned perpendicular to this strike line, we need to rotate this lever in the back of this Brunton compass in order to adjust the clinometer level present in this Brunton compass. And while rotating that particular clinometer level, when we find the exact level or exact position where this bubble is at the center, we will take the angular data from this vernier scale or the angular scale given inside, and there is a long white pointer here that is giving me the value 30 degrees. So, I know the dip amount of this foliation plane is 30 degrees. Now, I need to measure the dip direction. For that, we will again follow the right hand rule. What is? I place my right hand here and I know thumb is towards the strike, then immediately I know the rest of my fingers will be directing towards the dip direction. So, I again place my Brunton compass horizontally. We know how to measure the horizontal plane by placing the bull's eye exactly at its center, and then this long side of the Brunton compass towards dip direction, and I get the dip direction is 030. That means the north point is pointing towards or directing towards northeast. So, together I have collected the data. Strike is 300 and the dip direction is towards northeast and the dip amount is 30 degrees. So, this is the geometric orientation of this foliation plane.
Now, we will learn how to measure trend, plunge and pitch. Again here instructions. So, you have to identify first the linear feature and so on, and then you have to use the Brunton compass in a different way that you have used to measure strike, dip and dip directions. And then you measure also different features of the lineations, particularly plunge and pitch. However, again we have a demonstration for you that we have measured directly in the field. So, have a look here as well.
We are going to measure the different parameters or field data about the lineations that we saw. So, as you can see, this is an intersection lineation, or more precisely I can say that this is a striping lineation, because this is the trace of the bedding plane on the S1 surface or the foliation surface. So, this intersection lineation, this is a linear feature. That means we need to measure two different things, which are trend and plunge of a lineation. So, in order to do that, we need a special device, a field equipment known as Brunton compass. We have this Brunton compass. I am opening the Brunton compass now here. So, there is a dial. So, this dial is the compass where we measure the direction or the trend, and there is a clinometer level or clinometer compass which gives me the amount of dip or plunge. Now, in order to do that, there are two spirit levels. One is the bull's eye to measure the horizontal level, and another spirit level which is attached with this clinometer scale, which gives us the perfect dip amount or the plunge amount. Now, for measuring the plunge amount of this lineation, we should put this Brunton compass. There are two edges, you can see one is this edge and another is this edge. So, these edges are flat. So, we put that exactly vertically on the lineation along the direction of plunge, and this long axis, it should be pointing towards the plunge direction, and the mirror should be in the opposite side. And now, for measuring, what we have to do, this scale, this clinometer scale is actually rotatable, and we need to rotate the clinometer scale using this lever attached behind the Brunton compass. As you can see, when we are rotating this Brunton lever, the spirit level here attached with this cylindrical spirit level is actually moving, and when this is actually happening, we can see that the reading comes 15 degrees of this clinometer scale. So, the plunge amount measured on a vertical plane of this striping lineation is 15 degrees. Now, you can say that it is like a vector, that means it needs a direction. So, for direction, we need to measure the trend of this lineation. For measuring the trend of this lineation, what we need to do, we need to place this Brunton compass just horizontally on the surface of the lineation, and there is the bull's eye. As you can see, this bull's eye, we need to bring the bubble exactly at the center of the bull's eye. When that bubble is in the center, that means the compass is horizontal, and then alongside should be pointing towards the plunge direction, and then what we need to do is to get the north pointed reading on the compass dial, which gives me a direction 320 degrees. That means this lineation is plunging 15 degrees towards northwest. We are going to measure more data of this crenulation lineation. So, there is a very beautiful exposure we are seeing here, and we are going to measure the trend and plunge of these crenulation lineations. So, for that I am going to place my Brunton compass vertically on this crenulation lineation, and I am going to adjust the lever present at the back side of the Brunton compass in order to bring the bubble of the cylindrical spirit level at exactly in the center. So, while doing that, you have to adjust the clinometer level constantly to see where this is coming, and now it is in the center, and the plunge amount is 20 degrees. Now, I measure the trend of the plunge like this, and as you can see that this lineation is plunging towards this direction. So, I point the long axis of Brunton compass towards this and the mirror away from me, and accordingly I measure the bull's eye spirit level. It is perfectly centered, and the north point reading is 100. So, the plunge of this lineation is 20 degrees, plunging towards 100.
Now, we will see how to note these data in your lab book, or how to record them in the lab book. And I tell you that there are different styles. You may follow a single style and learn a single style. However, if you have to read others' data, then you probably have to know what are the different styles. People are trying to converge to a single style, but there are different schools and they measure it differently. So, what we are going to do now, or we are going to learn here now, are mostly the conventional way. So, usual convention is first you note strike, then dip angle, and then dip direction. Now, while we note this, there are two very important things to remember. First, for the strike, what is the range of strike? 0 degrees to 360 degrees. That means, a strike value can be maximum of 3 digits. So, does not matter whether your strike that you are measuring is 2 degrees, 22 degrees or 222 degrees, you always define it as 3 digits. So, if it is 2 degrees, then you always write 002. If it is 20 degrees, if you write it 022. In contrary, if we consider dip, then we have learned that it goes from 0 degrees to 90 degrees, from horizontal to perfectly vertical. So, the maximum digit that we use here are 2 digits. So, does not matter if your strike is 3 degrees or 33 degrees, you always define it with 2 digits. So, strike must be written in 3 digits, that is 078, not 78. And this is how we write the strike. So, assume a bedding plane has a strike of 120 degrees measured following the right hand rule that we have seen, and dip angle is 45 degrees, then we write it either this way or that way. In the map, we define strike. So, this is defined considering this is your north direction. So, this is 120 degree strike line, because this one is 120 degree and it is dipping towards southwest. You make a vertical line and place the digit 45 degrees. So, if someone has to read, then by looking at this orientation in the map, one can understand that this is the strike line and the planar feature is dipping towards this side. This is north, this is east, this is south, this is west. So, it is dipping towards southwest, but you have to define what is the magnitude of the dip angle. So, here you write this, and this completes the description of the strike and dip direction in your map. If you have a overturned dipping bed, you define it this way. If you have a horizontal bed, you define it this way, and if you have a vertical bed or vertical planar feature, you define it that way, where the long line or longer line is the strike and the shorter line is the dip. Now, for trend it is relatively easier, because you have to note only 2 data, one is plunge and another is trend. Again, plunge is 2 digits and trend is of 3 digits, right. So, you define it always as 2 digits slash 3 digits with degrees. Okay. So, first you note the plunge and then you note the trend and separate them by inclined slash. So, trend must be written in 3 digit numbers like 078, not 078, and if we have a linear element that has a trend of 80 degrees or 080 degrees and it is plunging 56 degrees, then we write it either this way or that way. Okay. And in the map, again the plunge we can define, because map is horizontal. So, you can put the azimuth in a very simple form. So, this is 80 degrees. If I consider this is north, this is east, this is south and this is west. So, this angle it is 80 degree. Okay. So, the line goes like this, and towards which it is plunging, you add an arrow, but you have to give the plunge value, and that is this value is 56 degrees. So, this is how you note the dip, strike, trend and plunge in the field. In this lecture, we will be having different types of planar features. We will be having different types of linear features, particularly when we refer to the superposed fold. So, we will follow some nomenclatures, and in the field we will refer them accordingly, and at the same time we will note them in the notebook and plot them in the map in the same fashion. So, always we refer primary bedding plane as S0, that means sedimentary layers. Whenever we see them, we will measure and we will always refer them as S0, and successive deformation planes would be referred as S1, S2 and S3. That means S0 is developing S1, S1 is developing S2, S2 is developing S3 and so on. That is a very straightforward way to say, but we will see how it goes. In a similar way, we will not say F0. So, this is just a terminology to talk about. There is no F0, that means there is no fold, but first fold axis we always define as F1, second generation fold axis we define as F2, third generation of fold axis we will define them or we will refer them as F3. In a similar fashion, the deformation corresponding to the development of F1, F2 and F3 would be referred as D1, D2 and D3. So, these are the standard nomenclatures that we will be following in the field or in this lecture series. So, with this I finish this lecture, and in the next lecture what we will learn that how to record these data in a stereo net or how to plot these data in a stereo net, and we will see there are techniques. So, planes we will refer them as lines and lines we will refer them as points in the stereo nets. So, to understand that, it is very important that you have a very clear idea about stereo nets, and we will be learning this in the next lecture. Till then, stay safe. Thank you.